both my regular viewers will be aware that I'm in the process of preparing this brand new Rotax 582 to go into my streak shadow to replace the somewhat superannuated 532 that was in it before. One of the unexpected consequences of that is that I need to change the tacho, because the tacho that was in the aircraft previously that worked with the 532 won't work with the 582. In the process of choosing a new tacho, I thought it would be nice to have an hour meter, because the aircraft has never really had an hour meter. So I started looking for tachos that include hour meters. The Rotax tacho for the 582 doesn't include an hour meter. And anyway, one thing led to another, and I ended up with this. This is MGL Blaze EMS2 engine monitor. So this is a digital tacho and an hour meter, but it also does a whole load of other stuff. So actually it can replace all of the engine instruments that I've got. So my fuel gauge, my temperature gauges. I'll do a full review of the Blaze when I've had chance to fly with it. The Rotax 532 and the 582 are pretty simple, really, in the parameters that you can actually monitor. So you can monitor engine speed using the tacho, how fast it's going round. You can measure exhaust gas temperature, and that tells you something about how efficiently and how effectively the combustion in the engine's working. And you can measure water temperature, because obviously the 532 and the 582 are both water-cooled engines. And that's it, really. You haven't really got very much else. First things first then. So we've got two types of engine temperature sensor. This one is a coolant temperature sensor, and this is actually a thermal resistor or thermistor. So the idea of this thing is that as its temperature changes, then its resistance also changes. Now this is an exhaust gas temperature sensor, and this is actually a thermocouple. Now a thermocouple is a peculiar type of sensor. Now hopefully you can see that we've got two little wires that join together at this little bead. Now I always kind of assumed that the little bead was the sensor. For the sake of full disclosure, I have to say I've been working with thermocouples for years in a professional capacity, and it had never really occurred to me to wonder how they actually work. And actually, it's the wire itself which is the sensor. So what we've got here is two different types of nickel wire. The reason it's two different types is that they're mixed with other metals to create one that's got a bit of chromium in and one that's got a bit of aluminium and manganese and things in. So they're slightly dissimilar metals. And the way the sensor works is that as you warm it up, it generates a voltage. What the thermistor does is as you warm that up, it changes its resistance. As you warm this chap up, it creates a voltage of its own. So the principle and the gauges that you need for these things are rather different to one another. So here's our gauges. So we've got our water temperature gauge and we've got our exhaust temperature gauge. If we have a look on the back of them, so on the back of the water temperature gauge we've got three terminals. So we've got a plus and a minus, or plus and minus, for supplying power. So that's connected across your 12 volt supply. And then we've got a signal terminal. So we're putting power in, we're putting 12 volts in, and then we've got a connection for signal. On the back of the exhaust gas temperature gauge, now bear in mind this is a double gauge, so we've got two needles because we're measuring two lots of exhaust gas temperature. So on the back of this we've got four terminals. So two of them connect to one of the sensors and the other two connect to the other sensor. Now what we haven't got is we haven't got any connection to power. So there isn't a 12 volt power connection to this. So, well, there must be magic going on, mustn't there? Because the gauge works, but we're not actually supplying any power to it. And the reason for that is that all of the voltage that the gauge uses comes from the thermocouple. So the thermocouples generate the electricity, and then this little gauge is actually just a very high precision voltmeter. So one word of caution if you're playing around with these things is you must never connect them to 12 volts. So you must never connect a 12 volt supply across these terminals, because this gauge is designed for measuring up to about 25 millivolts. If you supply it with 12 volts, then it's going to send the needle all the way to the top and will damage or potentially damages the internal workings of the gauge. Right, so what we've got here is 2 cups of water. This one has got hot water in it. This one's got cold water in it. At whatever the ambient is in here, about 15 degrees probably. So I've got my thermal resistor, and at the moment my multimeter is set in the millivolt range, so it's measuring a voltage, and you can see that it's measuring about 0.1, about 0 millivolts. So if I put this sensor into the hot water, nothing very much changes. And if I put it back into the cold water, it's still about 0. So this sensor isn't generating a voltage all by itself. If I change the multimeter over and I put it into the resistance scale, so there we're on the 20 kiloohm scale. So at the moment it's showing, what's that, about 2.6, 2.7 kiloohms. So if I drop it into that cold water, just move the thermometer over, so you can see the resistance is going up. The thermometer's taking a little while to catch up, and because the sensor's been in the hot water and is a little bit warm, it's taking a while to cool down, but it's getting back down to ambient now. So we're down about just under 15 degrees, and we're showing 3.4 kiloohms. So if I go back over to the hot water and pop it in there, you'll see that the resistance starts to drop quite quickly. So our water temperature, we're up at about 70 degrees, about 70 C. The reason this is taking some time is because obviously there's a fair amount of thermal inertia in the sensor itself. We've got this big lump of brass, and it takes a while to warm the big lump of brass up. So there you go, we're down about 3/4 of a kiloohm, about 750, 746 ohms now. So now I've connected our temperature sensor up to the gauge, and you can see that the gauge is reading just under 60 degrees and the thermometer is reading just over 60 degrees. So there is some discrepancy, and we don't really know which way around the discrepancy is. I mean, my 99p coffee thermometer might not be entirely accurate, but also my 30-year-old temperature gauge might not be entirely accurate either. But you can see that if I take it out of the hot water and drop the sensor into the cold water, you can see that the temperature gauge drops down reasonably quickly. There is a delay, and that delay is because of the time it takes for the temperature sensor itself to cool down. Now, of course, when the gauge is measuring engine temperature, you've got a great big thermal mass in the engine itself, all the metal in the engine, and also all of the water in the cooling system of the engine. So the fact that the sensor itself has some lag in it doesn't really cause you any problems, because the temperature of the engine can never really change faster than the temperature of the temperature of the sensor. So what I've done now is I've hooked up the multimeter between the ground terminal and the signal terminal on the back of the gauge, and the multimeter is in the volts range, it's in the 2 volts range, so we're measuring about 0.18, 0.19 of a volt there. So that's between the signal and ground. So about 0.18. If I drop it back into the cold water, you'll see that the voltage difference starts climbing quite rapidly. So remember, what's happening is the resistance of the sensor is going up, so the voltage difference between those two terminals increases. So essentially what this gauge is just a clever voltmeter. So now watch what happens if I adjust the supply voltage to the gauge. So you can see this is showing the supply voltage. At the moment we're on 12.3 volts. And we're showing a voltage difference between the signal and ground of about 0.13, 0.128. So watch if I change the voltage now. So now my battery's going a bit flat, alternator not working or something like that. You can see that actually the reading on the temperature gauge and the voltage reading between signal and ground hasn't actually changed. And if I wind it up a bit, there you go, engine started, perhaps the alternator regulator's not regulating terribly effectively, but the voltage hasn't changed. So this is a slightly clever voltmeter, in the sense that what it's actually doing is measuring the voltage between signal and ground, not measuring its supply voltage. So next up's our exhaust gas sensor. So the exhaust gas sensor is a K-type thermocouple. At the moment I've got the multimeter set on the millivolt range and we're measuring 0. If I put that into the hot water, you'll see that pretty quickly it starts generating a voltage. Not an enormous voltage, but you can see there we're generating 2 millivolts. And if I move across and put it into the cold water, you can see that that voltage drops back down again. So in the hot water we generate a voltage, and in the cold water we can get the sensor to reach the water, we generate less voltage. So if I move across to the resistance range, so I've gone over to the 200 ohm resistance range and put it in the hot water, you can see that the resistance changes as well, because actually resistance of all conductors changes with temperature. So the cooler your conductor is, the lower its resistance is going to be. But that's not the operating principle of this sensor. This is an exhaust gas temperature sensor. The maximum temperature your exhaust gas is supposed to get up to in the 582 or the 532 is 1200 Fahrenheit. So our hot water at the moment is at 140 Fahrenheit. So obviously this sensor can go a lot higher. Time for a different experiment perhaps. So what I've done now is I've put the exhaust gas temperature sensor into a hot air gun. And the hot air gun runs at 530 centigrade, which is just under 1000 Fahrenheit. So at the moment we're at room temperature. You can see that that is cold at the moment. When I turn the hot air gun on, we'll pretty quickly get up to 530 centigrade. So if you watch the voltmeter is climbing up pretty quickly. We're still in the millivolt range, so that's reading in millivolts. So now for some maths. So We know the output of the thermocouple because that's a constant. So the output of the thermocouple is a constant 41 microvolts per degree centigrade. So we're up about 22 millivolts. So if we divide 22 millivolts by 41 microvolts, we get about 536, 537 degrees centigrade, which is about what we expect that hot air gun to be producing. There's a couple of important points to bear in mind when you're connecting these cables, so when you're connecting your thermocouple cables. The first one is that they can't be soldered. So when you're connecting them, they're normally just crimped. You can join them by spot welding, but if you're normally if you're making a connection, you'd crimp something to it and then you'd connect that. The other thing to bear in mind is because of the principle on which the thermocouple works, the type of wire that you connect to is important. So you can actually get thermocouple extension wire. So thermocouple extension wire is different to thermocouple sensor wire, but you should be using thermocouple extension wire between the end of the thermocouple wire and whatever gauge you're using. If you look at the way I've connected the meter to our sensor, you can see that I appear to be back to front. So I've got a white conductor and I've got a red conductor. I put the negative probe onto the red conductor and the red probe, the positive probe, onto the white conductor. Bizarrely, the standard for thermocouples is that the negative wire is always the red one and the other coloured wire is the positive one. That's kind of important because that means that actually the polarity of these things when you connect them makes a difference. So now I've reconnected the probes the other way around, so now I'm black probe to white wire and red probe to red wire. You can see that I'm reading a negative voltage. Now that would make your gauge read the wrong way around, so as the temperature increased, the reading on the gauge would go down, not up. One of the common complaints that I hear quite often about Rotax engines, the two-cylinder Rotax engines, is that the exhaust gas temperature is different on the two cylinders. Exhaust gas temperature can be an indication of the fuel-air mixture and how rich or lean that is. So if you've got different exhaust gas temperatures in the two cylinders, then that indicates that you've got a different mixture in the two cylinders, which tends to indicate that you've got a carburettor problem and that you need to adjust the two carburettors to match. But one thing to check before you start doing that is to make sure that actually the instrument itself is working properly. So it's possible to develop faults in both the sensors themselves and in the gauge. So what we've got here is an experiment where the two sensors are set up in the hot air gun. They're reading side by side, so they should be reading exactly the same temperature pretty much. So you can see that even though the two sensors should be reading exactly the same temperature because they're both reading in pretty much the same position, you can see that one of them is reading 1300 Fahrenheit and the other one's reading about 850 Fahrenheit. So they can't both be right. So what we're going to do is swap the leads over and see if that temperature difference follows the sensor or not. So you can see now that the left-hand gauge, or the right-hand scale if you like, is reading nearly 1500 Fahrenheit and the left-hand scale is reading, well, just under 1100. So the left-hand side of the gauge is reading about 300 degrees lower than the right-hand side of the gauge. And that difference stays the same even when we swap the sensors over. So that suggests that we must have a gauge problem because the reading follows the gauge connection. If we had a sensor problem, we'd see that as we swap from one side of the gauge to the other, then the high temperature would follow the sensor connection. So as we swapped over, we'd see that we'd go from the right hand side reading 1500 to the left hand side reading 1500. Now you can either do this experiment on the bench with a hot air gun, or you can do it in flight just by swapping the sensors over on the engine. If you've got a cylinder that's reading high, if you swap the sensors over on the exhaust manifold, you still end up with the same needle going high. If you do, that's an indication that actually it's the gauge that's reading wrong and not a problem with the engine itself. So what's all the fuss about in the first place? Well, actually it's very simple, and it comes down to this. See, the MGL Blaze sets up its own display depending on what channels you tell it you've configured. Now, it's set up as standard to have cylinder head temperature, and cylinder head temperature uses a thermocouple. But if you put in your thermistor based coolant temperature sensor, you have to put that in as one of the analog channels, and what that means is that it scrolls backwards and forwards between fuel level and coolant temperature. So you see, if the gauge is configured with a cylinder head temperature sensor, you don't have to put up with these analog sensors scrolling backwards and forwards between temperature and, in this case, fuel level. So what I'm going to have to do is swap my thermistor based coolant temperature sensor for one that's based on a thermocouple, so that I can have it displayed as CHT on here rather than have to have it scrolling. Simple as that. Thanks for watching. This video's turned into an homage to this old Tony. I'm also available for hand modelling if anybody's interested. Safety gloves, industrial hand cleaners, those kinds of things.